welcome to the Physics Lounge. We're taking a look at the Level 2 Physics and Mechanics exam for 2022. And I'm on holiday in someone else's home, so I'm not sure I might get interrupted along the way, but we'll see. So, first question, kinematics, projectile motion. A steel ball is held 40 centimeters above a table and it's dropped, and the time for it to fall to the table is measured. Calculate the time it takes for the ball to fall to the table. So kinematic equations, initial velocity equals 0. We're trying to find the time. We know the distance that it travels, which is 0.40 meters. I'm giving it in SI units rather than in centimeters. And we know G, the acceleration due to gravity downwards, is 9.81 meters per second. Not sure if it uses 9.8 in the resource booklet, but yeah. One little trick with this, I'm using down as positive direction, so my displacement as it drops will be positive in the downward direction, and the acceleration due to gravity will also be positive in the downward direction. So what we have, D equals VIT, it's half AT squared. So we've got acceleration, we're trying to find the time, initial velocity is 0, so that term cancels, rearrange for T. The experiment was repeated with another ball of the same size but half the mass. Ignoring any effects of air resistance, use physics principles to explain how the time for the second waterfall compares to the time for the first. From your equation here, does any of it change? D is the same. Acceleration is the same, so therefore time will be the same. So they're all the same because the force due to gravity and therefore the acceleration due to gravity is independent of the mass. Well, I should say the force due to gravity isn't actually anything about it. A larger mass means you'll have a larger force, the same force due to gravity, but that's the reason why the acceleration due to gravity, rearranging for G, stays the way that it does. Fg over m, if you increase m, you're increasing Fg by the same amount, and therefore gravity doesn't really change. This is a neat question. It more naturally would perhaps fall into level 3, I would feel, but still, that's okay. It's not just using either the equation above or using F equals mg and explaining how as mass increases, force due to gravity increases for the same acceleration due to gravity. Anyway, the steel ball is now rolled along the table and off the edge, so we've got half of a parabola. Height of the table is 0.70 meters, so they're trying to get you to have that extra step of doing a conversion again. The ball hits the ground 1.8 meters past the edge of the table. Calculate the ball's final vertical velocity, so vertical and horizontal can be separated for projectile motion. So this vertical velocity, Vf, just for the vertical motion, if we consider the vertical, it's basically dropping straight down with the final velocity that we're trying to find out. We don't know the time. The initial velocity vertically is still 0. Just in the vertical, again, vertical. Remember, you can separate those. Acceleration due to gravity is still down at 9.81 meters per second squared. What else do we have? D. Displacement or the height is 0.70 meters. So we're looking for something. We don't actually need the time if we're trying to find the final velocity, but the time will be relevant for the horizontal, no doubt. What have we got? V F equals, that requires time, Vf squared equals Vi squared plus 2AD. That's the kinematic equation. There's no time involved. You know the acceleration, you know the displacement, initial velocity is 0, so you'd square root that to find the final velocity vertically. What What assumption have I made? Probably the air resistance. No, there is no air resistance. That's probably the only assumption that you can really make. Maybe there's something else. Let me know in the comments if your teacher has taught you something different, or if you're a teacher and you teach something different. It's a bit of a pointless question if it's just air resistance, because that's already mentioned above. So anyway, maybe there's another assumption. Calculate the size. Maybe we just say there's no other forces more generally except for the force due to gravity. That would probably be, unless I missed something in the reading of it. Yeah. Okay, calculate the size and direction of the velocity of the ball just before it hits the ground. Start by showing the horizontal velocity of the ball is 4.8 meters per second. So just checking to see what information they've given us. So we need the time, really. If we know the time that it takes to fall there, we can work out the time during which it follows this 1.8 meters, and then we can work out the horizontal velocity. So we'd probably find the time of flight in the same way, or you could use this, any equation really, because you've got VF, you've calculated above, you know A, you know the initial velocity is still 0, so you can find that time. Once you know the time horizontally, there is a constant velocity, because we ignore air resistance and there's no other forces acting on it except force due to gravity, which is in the downward direction. So that doesn't change the horizontal velocity. So time of flight being whatever you calculated from above, and the distance being 1.8 meters. That's from the diagram above as well, 1.8 meters. So final velocity, velocity equals distance over time, and just put in your 1.8 over whatever the start was, the calculation there. Now that you have your horizontal velocity, you add it to your final vertical velocity, and you'll have the overall velocity of the ball, the overall velocity of the ball just before it hits the ground. Probably makes most sense to have this angle, so you'd work out that angle as well. So if you know this velocity being the horizontal velocity, and you've got the final velocity vertically, you would add those two together, sums of the squares square rooted to get this, and then work out the angle using a bit of trigonometry. So question 2, momentum and impulse. Two cars set up with a spring between them. The spring is compressed by 10 centimeters. When the spring is released, the cars rapidly move apart in opposite directions. The spring is a spring constant of 250 newtons per meter, so 0.1 meter that it's compressed. That's your x. K, or your spring constant. I'll just call that K like that. That's probably easier. Calculate the total energy. E equals half kx squared, so just plug your numbers in. The mass of the red car, 0.5 kilos, blue car, 2 kilos. So it's good that I've labelled them for those who are colourblind. The final velocity of the blue car is 0.5 meters per second. Calculate the final velocity of the red car. Okay, so they should be equal and opposite. This is an explosion situation. We're assuming that they are motionless to begin with, and so momentum must be conserved, so P red equals P blue, but in the opposite direction. So blue, you're told, well, you know the masses of both, and I'll just red, red, blue, blue. You know the velocity of blue, the mass of blue, you know the mass of red, so you can rearrange to find the velocity of red. What assumption have you made? Be conserved. No external forces. The only forces acting are the ones due to the spring acting in both directions on those two. In a different experiment, the red and blue carts are set moving in opposite directions with equal momentum. Blue carts stopped at the end of the track by a solid board, and the red carts stopped by a padded wall. Use physics principles to explain whether the blue cart or the red cart will suffer the most damage as they both stop. Now this is a bit tricky because they have different masses. In the real world, you're going to have different effects depending on the thickness of the board and all of that. So in some senses, if you're being a little bit particular, you're going to have problems answering this question. But if you don't overthink it and you just realise, they're trying to get at the old change of momentum equals F times the change in time. They both have the same change of momentum. One of them is going to have a longer time, therefore a lower average force acting for the same change of momentum. So that's the padded one. It will take longer time, so there'll be less force and therefore less damage. Okay, it would have been better to say two carts that are exactly the same. Anyway, the 2 kg blue cart moving at 2 meters per second, so it's 4 kilogram meters per second. Took 0.02 seconds to stop. State Newton's third law of forces in the context of the collision of the blue cart and the solid board. So for a reaction force, an equal and opposite reaction force. So in this case, you've got the action force of the wall trying to slow the cart down. So when it hits the wall, at that point, wall cart, you've got a force in that direction and a force in that direction. One's the force of the cart on the wall, the other's the force of the wall on the cart. That's your action-reaction pair. And that's easy enough to sort of state, but practical terms, what really happens? The force of the wall on the cart is going to cause it to decelerate and potentially change shape if it's getting damaged, or it might bounce back if it's an elastic collision and just conserve and go back in the opposite direction with the same amount of. Or you could say that momentum from the cart will be imparted to the wall, which is connected to the earth, and just change the rotation ever so slightly to compensate, something like that. There's all sorts of directions you go in. Really interesting to overthink that one. But basically, action-reaction forces, calculate the size and direction of the average force experienced by the solid board. F times change in time equals change in momentum. Calculated the momentum for over there above. 0.02 seconds for the time, rearranged for the force. Don't forget Newton's and direction. It's the direction of the average force experienced by the solid board. So the direction of the force experienced by the board is going to be in the direction that it hits, assuming that the cart is coming in that direction, hits the wall, and then, draw a diagram to show if in doubt. Question 3, forces. Calculate the spring constant for a spring that extends, we're back to springs again, extends 200 millimeters, 0.20. It's really one significant figure when it does that, but we'll go up to 3 just because this is 3 as well. When extends that by that, that's our x value. When a 2.94 Newton weight is hung on it, providing 2.94 Newtons, so F equals kx. We're trying to find k, so you just rearrange there. I don't think there's any tricks in that. Just make sure it's the extension and not the length of the spring. So sometimes you might get a diagram, and you've got your mass hanging on it, and they just give you the full length, but you're expected to take away the length of the spring before it's stretched, and your extension is actually only the stretched distance. The diagram's a bit shoddy, but what I'm saying, hopefully. Block is attached to 2 identical springs and hung from the ceiling on the diagram below, add labelled force arrows to show all the forces acting on the block. Force due to gravity, force and force that are equal and opposite on the of the springs, because these are the forces acting on the block, the force of the block acting on the springs. Now, if you're doing this very particularly, that'll be twice the length as the height there and there. So that distance on your force arrow and that distance on your force arrow should add up to the total distance vertically there, because all the vertical forces are balanced. We're assuming that it's motionless, not bouncing, so it's a constant velocity of 0, therefore the forces are balanced. Draw a labelled vector diagram to show how the three forces acting on the block add together. Force 1, call that 1, force 2, and Fg can be 3. And that's 0 net force, because they all add up to get you back to 0. An athlete in training holds a uniform rod. That's a bit of a jump all of a sudden. Normally they would try and give us maybe one of the forces at 2, and you use that with 90 degree or a different angle to work out what the force of 3 might be. But anyway, an athlete in training holds a uniform rod 2 meters long, stationary in a horizontal position. The mass of the rod is 3 kilos. So the mass of the rod acts down through the center of the rod, which is 1 meter from either end. Just to put that in the diagram, calculate the forces FA and FB that are required by the athlete's hands to hold the rod in equilibrium in the horizontal position. So, does it say the weight of the rod? The mass of the rod is 3 kilograms, so that's 3.0 times by 9.81, or again, whatever the value of gravity is in your resource handout. So it's approximately 30, just to give you that. So, and you've got 30 centimeters, 0.30 meters from there, so that's 0.70. I would probably naturally take FB as a pivot point. And you've got the force due to gravity on the rod pulling down over here, and the force A here to create equal and opposite torques. And so, yeah, and FB acting upwards equals the force A downwards plus the force of the rod. So, yeah, we're trying to solve for FA and FB, but this is a case of some of the torques equaling 0, some of the forces equaling 0. So some of the forces equaling 0 is probably the most straightforward one, FA plus FB plus that about 30 newtons, which is that force due to the rod. So it's just purely vertical forces, not talking about torques. So that we have 1 that we know and 2 that we don't know. Then when we're dealing with the rotation, if we take our pivot point again about FB, the distance from FB is 0, so that removes FB from the equation. So we should have FA times by the 30 centimeters, 0.30 meters. That's 1 torque rotating that direction, and then the torque rotating that direction. So we'll make it that positive and that negative. And in that case, this should probably have been FA minus FB plus there. And then down becomes positive, and awkwardly up becomes negative. Probably should have done it the other way, but flip your page upside down if you like. It's totally arbitrary for the sake of working out those numbers. I hope I didn't confuse you there, but in any case, if going back to the torque equation up the top, the sums of the torques are 0. FA here times by the distance, 30 centimeters, 0.30 meters, creates the torque going in one direction, and then in the other direction you've got 0.70 meters times by that approximately 30 newtons. 30 times by 0.70. And so that's an easy one because you've got one equation with one unknown. I'll put a question mark there instead. You can rearrange that part to solve for FA, and then you substitute FA into here and rearrange and solve for FB, and now you know both of those forces. Okay, there's a little bit garbled and slow, but that's that. On the last page, D, a jelly is placed on the edge of a plate. Woohoo, jelly. And the plate starts to spin, so the jelly is moving in a circle. As the plate speed increases, the jelly initially maintains its position at the edge of the plate until it eventually slides off. Okay, so it maintains its position because there is enough force due to friction holding it in place and to cause it to rotate. So the force due to friction is towards the centre. That causes the jelly to accelerate towards the centre. So that's your force and centripetal force, which is proportional to the centripetal acceleration. There's a point where there won't be enough force supplied by the jelly, and therefore it can't accelerate fast enough. You say accelerate fast enough, can't accelerate at a rate enough to remain on there, so it'll slide off. It'll probably slide off gradually in a bit of a curve, and as soon as it leaves there, boom, straight. You know, from the that's very poorly drawn, but should be at right angles to the centre. But it'll curve initially and then go straight once it loses contact and you have no more friction. Okay. Anyway, try and draw that better like that. Use of physics principles to explain why the jelly initially stays on the plate. I just kind of did, but as the speed increases, it slides off. Also did that. Okay. And the answer should include naming of any relevant forces involved. You get centripetal force. We did that. How increasing the velocity affects the situation. So increasing the velocity means a larger FC is required to cause the acceleration required to change direction. And then description of the path would take when it first slides off. Well, we've described it curved, and then once it releases from the plate, it's going to go off at a tangent to the surface, a tangent, which is at right angles to the radial position. Okay. I don't know. I feel like you could have snuck in a little bit about constant velocity. Constant speed for velocity in there. You know, the classic. How can it change? Go at the same at a changing speed. Changing velocity while speed doesn't change. And just to refresh your memory and take the opportunity there, the speed can be constant because speed doesn't include direction. But as soon as you include direction, direction's constantly changing. So velocity being a vector, magnitude and direction. The magnitude doesn't change when the direction does, therefore an acceleration is required in the direction of velocity change, which is towards the centre, etc., etc. Okay. I think that's the end. Yep, sphere diagrams. So fairly straightforward paper, I think. I don't think there's anything too out there in that. I like the jelly question because I like jelly. That's probably a good place to leave it, actually. Yeah. If you found this helpful, please do share it with others in your class or other teachers. Like and subscribe and all of that kind of nonsense if you feel it's helpful. And always happy to receive feedback. But being a very busy person, don't always get time to get to it. Feel free to put your favourite flavour of jelly in the comments. Cheers.